Okay, so last week we didn't have the lecture due to this timetable variation, but you did have the problem set one, and I have marked some of them already. Actually, I'm happy. So seems like you guys are more prepared this time around. I'm not sure, or it's easier this time. Have no idea, but anyway, that's good. So hopefully we get this marking done very soon, but there are lots to be marked, so yeah, just be patient. Okay, so for this week it is about producer theory. So we start with the production. So pretty much for the producer theory, the way that the producer optimize finding the profit maximizing level of output, or finding the cost minimizing amount of labor and capital would be like similar to the consumers maximizing utility or minimizing the expenditure. Very similar. It's just a slightly different setup, and there were some parts that were slightly different or have a different interpretation or meaning than with the consumer counterparts. Okay, so we start with the production. So as soon as you guys already watched the recording, so we're gonna go quickly with the production and isoquant, right? So we assume that we are dealing with only two inputs, labor and capital, L and K. Let us assume that we have a production function. So Y, which is the amount of output, depends on this amount of two inputs, labor and capital, right? So you can see it's like a similar to the utility function, right? When utility is equal to, some function that depends on the amount of good X and the amount of good Y consumed. But now instead, this is going to be inputs, and this is going to be output. So in the consumer theory, right, when we talk about utility, and like I say, utility is equal to a certain particular number, it actually doesn't give you that meaning about like how big, how happy they are, right? It just gives you just the idea of preference ordering, just that the bigger the number, that means that the higher, the happier you are. That's it. But you cannot say that when utility is equal to 2, for example, versus the utility equal to 4, that means that when you have utility equal to 4, that is twice happier than when your utility is equal to 2. It just tells you that when your utility is equal to 4, you are happier with that bundle than the other bundle with a lower level of utility. However, in the production function, right, with the production function, it actually have the meaning. This one is gives you the units of output, right? So if you plug in some the values of inputs into the production function, it would give you actually how many outputs that this firm can produce based on the certain amounts of these input combinations L and K. So that is the main difference when we talk about utility function versus the production function, right? The production function that gives you the value, that value actually means the output units, right? So if what in this case, if Y, now Y is means output in this particular context, in the producer context, Y is output, which is different from Y, as you know, the consumption bundle of X and Y. Right? So this Y is an output. So when Y is equal to 2 versus another Y that is equal to 4, now it actually means something. So in this case, when Y equal to 4, that means that the output is twice more than the output when Y is equal to 2, right? When Y equal to 4, etc. So, so when we try to derive the indifference curve, remember that indifference curve is the bundles of good X and Y such that the consumer are indifferent to between all the bundles along the same indifference curve. So we fix utility value. Similar to the isoquant. Now with the isoquant, we work with the contour lines of the production function where we fix the amount of Y or the amount of output right? In this context, so we fix the amount of output and we try to find what are the input combinations that, you know, that would yield the same level of output, or, you know, what are the input mix L and K that, you know, that could just produce the same amount of output. You maybe, you know, to produce 10 units of output, you may either being quite labor intensive by using only 1 unit of K and 10 units of L, or you can be a capital intensive to produce same amount of output by using like 3 units of K and maybe 5 units of L and so on, right? So that is the idea of isoquant. So with isoquant, we generally label the horizontal input variable as a label L, and the vertical variable is labeled as K or capital, right? So any contour like Y1, Y2, and Y3 would represent the different level of output. And as every bundles here, not bundle, our input combination here and here along the same in the isoquant would yield the same level of output Y1, for example. And you would imagine that it would make more sense, right? That if you increase, let's say from this point, if you increase both L and K, then your output should increase. Therefore, when you shift the isoquant outward like this away from the origin, then it should means higher level of output, like similar to the monotonic preference, right? When you have monotonic preference, then you increase X and Y, then your indifference curve will shift further out, and that means higher level of utility. But in the sense of in the sense of indifference curve, you would require the preference to be monotone, right? To have a increasing utility going outward. But for the production function, for the isoquant, you don't actually need that preference, because it's just like, you know, when you increase inputs, generally the output should increase, right? When you increase both input, all of the inputs, the output would increase. But would it increase at the same rate as you increase L and K, or it would increase at a higher rate, or it would increase at a decreasing rate? So that is that would require the knowledge or the application of the increase of the returns to scale, increasing, decreasing, and constant return to scale, which we will talk a little bit towards the end of this lecture. Okay, so we just know that when both K and L, right, when we have more K and L, of course there would be more output. Let's say that if I draw the diagram like this, right, let's say this is K1, L1, right, that yields Y1. And then now I increase both K and L, right? Now at K2 and L2, right? Let's say that K2 is equal to 1.5 times K1, and L2 is equal to 1.5 times L2, for example, right? And that would give me Y2, which is supposed to be greater than Y1, obviously. Now what happened is this Y2 is equal to 1.5 Y1, or it is smaller than 1.5 Y1, or it is bigger than 1.5 Y1, right? We just know that it has to be bigger than Y1, but in which ratio? It will be greater than 1.5, or equal to 1.5, or less than 1.5, right? So that is that depends on the utility, the production function that would determine how big is this Y2 is when we increase K and L at the same rate, right? Okay, so let's look at the example that we have the production function, which is a Cobb-Douglas production function, L square root LK times K, right? So this is the same as square root L times K, okay? So to draw or to derive the isoquant function, right, we need to assume that all these, all combination of L and K must give you the same amount of output, has to be constant. This one has to give you a constant number. Let's say that we assume that the output unit is equal to 2 times square root of 3, right? This is our amount of output. We call it Y1, for example. We take the put this production function, and then what we would need to derive K as a function of L, right? Because to draw the iso quant, we need L on your horizontal axis and K as your vertical axis. That means that's like, you know, I mean, what you need is, we need iso quant function such that K or Y as a function of X, right? K as a function of L. So to get this, then you would get that. You would put, you would square both sides, right? Therefore, K is equal to 12 over L. So this is K as a function of L. So this is the function for the iso quant, right? When we assume that output is equal to 2 times square root of 3. And then with that, you can see that it is actually going to be a decreasing curve, right? A downward sloping, right? Because the slope of this function is negatively sloped, have an inverse relationship with L. So it has to be negatively sloped. And you can see that is the slope, the absolute value of the slope become smaller and smaller. So we just take the absolute value, right? So when L increases, actually, the slope becomes flatter and flatter according to this function, right? You can check that. Take the first order condition, which is going to give you a negative value, and then do the second order derivatives to check how the slope would change, right? And you can see that the slope would actually become the positive. So the first order derivative, K prime, would be equal to negative 12 over L square, right? So this is less than 0, right? Negative slope. And the second order derivatives, that would be K double prime, which is take another derivative of this function that gives you a positive value, would be 24 over L cube. Right? And this is positive. That's how we know that it should look like this, right? Because of this. K prime, K double prime. Okay, so you can draw the slope, draw the isoquant. So with this input mix, 112 or 26 or 62 of this input mix will yield the amount of output this much. And if we change the amount of output, let's say change to decrease to 2 times square root of 2 instead, then we have a different isoquant curve, right? With a different slope, so on, but it's gonna be in the same shape, but then it's gonna locate below the first isoquant. And if we increase the output, then we can get this isoquant at the higher level. Okay. All right. So any questions so far? Next, the marginal rate of technical substitution. So this is pretty much the slope of the isoquant. MRTS is just a slope of the isoquant. So you can either compute or find the slope of an isoquant based on this function, right? Based on this function, if you know the particular amount of y of output, and then you can derive, and you know the production function, you can derive the isoquant, you know, curve, and then you can find the slope of the isoquant, right? Based on this function. Or you can use the relationship of the slope of the isoquant that depends on the marginal product of labor and the marginal product of capital, which is what we're going to explore here. So with the marginal product of labor, MPL, pretty much it's just the partial derivative of the production function with respect to L. What does that mean? Right? This one is equal to that. What it means is the amount of output that is produced by one additional unit of labor input, right? Holding the other input constant. So let's say if MPL is equal to 5, what that means, but it could be constant or it could be not constant. Most likely it's not going to be constant, right? So but just for simplicity, let's say that you compute MPL it is equal to 5. What that means is that if I increase 1 unit of labor input, right, increase this by 1 unit, then my total output will increase by 5 units, okay, given that capital input is constant, right? And the similar, you know, interpretation could be applied to the marginal product of capital, MPK, which is a partial derivative of the production function with capital, right? That means when you increase K by 1 unit, how much is that extra unit of capital input could contribute to the increase in the total output, holding labor constant, labor input constant. Okay. So when we want to find the slope of an isoquant, right? Slope of an isoquant, that means that we need to control y, or the amount of output constant, right? Because it's on the same isoquant, right? That means that if let's say that I'm looking from, right, point A to point B, I want to compute the slope, right? So this is L, this is K, right? It's on the same isoquant. So this amount of LK and this amount of LK would give me the same level of output. So when I move from point A to point B, I would reduce the amount of K by this unit and increase the amount of L by that unit, and still give me the same level of output, right? If I change L by a bit, so let's say that change in L is equal to 1, right? Then how much does K have to change in order to remain on the curve, right? And that's what it is. So if the slope of isoquant, let's say, equal to 3, what that means, okay, -3 to be exactly correct. The slope of isoquant is -3. That means that if I increase L by 1 unit, right, I would have to decrease. If I increase L by 1 unit, this is equal to 1, then I have to decrease K by 3 units to be able to produce the same amount of output at Y1. Okay, so that is the meaning of the slope of isoquant. So whatever is equal to this, whatever the amount is, that means the amount of K that need to change in order to remain on the same curve, or in order to produce the same amount of output. Okay, so, and you actually can find the way to compute this slope, right? So we know that the slope of, okay, we start with production function, right? So we know that to move from point A to point B, there would be the change in both L and K, right? Because A to B, you can see that it moves to this direction. That means L has to increase and K has to decrease. So both K and L would change simultaneously at the same time. But still, this F, K, or L would have to be constant, right? So how do we do it? We cannot change K and L like at the same time when we do, you know, when we try to analyze this, we usually have to change one variable at a time and control the other one constant, and then swap it in another way around. So we will start with, okay, I start with right, holding K constant and change L. Oh, I think I'll do this better. Okay. Sorry, let's say that we fix L first and change K. So we are going down here, right? This is when we do going downwards here from point A, I call it point A prime. This is point A prime. From point A to point A prime, this is point A to A prime. From point A to A prime, L is held constant, right? It's the same L. At point A to A prime, it is the same L, but K is now reduced, right? So we are controlling L constant. We change K, right? So with that, we know, okay, K, this is MPK, right? So when we decrease K, right, then Y would decrease. When you decrease K, Y would decrease, right? So Y would decrease. So if you decrease K by 1 unit, right, Y would decrease by MPK unit, right? So you decrease K by 1 unit, Y would decrease by MPK unit. This is the MPK. So if you decrease K by this much unit, which is that much, right, then Y, the total change in Y would be equal to this. There is a total change in Y as a result of the change in capital, right? This is the change in Y when K changes by 1 unit. If K changes by this unit, then you need to multiply this amount of K that changed multiplied by the amount of marginal product that changed. That is result as a change in K by 1 unit, and that is the change of the output, right? The change of the output when K changes by this much unit. Okay, and then we have A prime to B. So now from A prime to B, right? From A prime to B, we hold instead the capital of K constant and allow L to increase, right? Same level of K, but more L. So in this case, K is held constant and we allow L to change. Again, this is going to be MPL, right? So when L changes by 1 unit, the output would change by MPL unit. But there is this amount of L that change. The L changes by this unit, this amount. So the total output changes as a result of the change in L would be this. Okay, so you can see that this one would be negative, right? So based on this particular setup, from A to A prime, you can see that this is going to be negative, and then from A prime to B, this is going to be positive, right? MPK is always positive, right? Always positive, but this one is a negative. This one is positive. So you have this negative and positive. So the total effect, because now we want to combine the effect of both K and L change. So we just like kind of consider in each particular, you know, scenario where we hold one variable constant and only let the other variable to change. So when we combine the effect A to A prime and A prime to B. So do you have the change from A to B, right? A to A prime plus A prime to B, that is a total change, total effect from A to B. And this total effect would result into zero change in the total output, right? So we have this is a change in the output as a result of a reduction in K. This is a change in the output as a result of the increase in L, right? So the total change combined has to be zero because the change in output has to be zero, right? Because it's on the same isoquant. So therefore we get this at A from A to B, right? So we have, I would just call it MP. MPK times change in K plus, do this, MPK times change in K plus MPL times the change in L has to be equal to zero, right? This plus this has to be equal to zero. So, or we can say that change in K over the change in L must be equal to negative MPL over MPK, right? And this is the slope, right? Change in K over the change in L is the slope of the isoquant, which is a function of negative MPL over MPK. Where can find K is positive? But Junji, I just saw the question from Junji. What I don't quite understand the question. Where can find K is positive? Oh, so you mean like if change in K is positive instead of negative? Is that what you mean? Okay, so let's say that you just move from point A to point B like this. So let's say I switch A to B, right? In this case, you're gonna have positive K and negative L, but you will not have the same directional change of K and L at the same time. Like, so if you increase K, you must decrease L. If you increase L, you must decrease K, right? And that's why you have a negative slope of this, because if you increase both K and L at the same time, you're gonna have more output. It cannot be the same level of output, okay? Okay, so here, so, all right. So this is how we also could find the compute the slope of the isoquant, which is negative MPL over MPK. This is where this formula come from, or you can use this, right? You can find the slope based on this isoquant function as well. Right? You just take the derivative. So in this case, K prime, that would be the slope, like K prime L would be, for example, negative 25 over L squared, right? So this is also, and should be equal slope of isoquant, right? Okay, so these are all equal. So then you get this. You get this. That is where this formula comes from. Okay, next, and with this, we just define this negative MPL over MPK. We call it MRTS, the marginal rate of technical substitution, which is the slope of the isoquant, right? Just negative MPL over MPK. So if you understand what the slope of isoquant is, you will understand what MRTS measures, right? So MRTS would measure the amount of K, right, that can be reduced when there is one more unit of L in order to produce the same amount of output. That's pretty much the slope of the isoquant itself. So let's say that if in the exam or the problem set, instead of I ask you to compute MRTS or the slope of isoquant, right? I just ask you like very simple like that, but instead I ask you, okay, compute the amount of K that can be reduced when there is one more unit. So by asking you this question, pretty much I just asked you to compute the slope isoquant, right? Because these are just the same thing. So don't get confused by just okay. But I don't know if I didn't ask you explicitly to compute the slope, then now you start to be wondering, okay, what exactly that means that you need to do. So actually that means you need to compute the slope of isoquant. So when study or learn this course, I don't want you to just like memorize things. You need to actually understand the meaning of all of those notations or those formula, where it comes from and how to interpret it, because that is actually more important. Use the intuition to actually understand it rather than try to memorize things, because when you understand it from the ground, really is a true understanding, then it doesn't matter how how I twist the question. Do you know what I want you to answer? Okay. Next, the law of diminishing marginal returns. Right? Diminishing marginal returns, and then there is another one, which is law of diminishing marginal rate of technical substitution. So don't get confused between these two things: diminishing marginal returns versus diminishing marginal rate of technical substitution. They sound similar, but they are different. Very, they have some similarity, but actually they are two different things. Diminishing MRTS, this is not the same. Okay, diminishing marginal returns basically is the same as diminishing marginal product. Okay, marginal return is a marginal product. Okay, these two are not the same. Okay, so for law of diminishing marginal returns, what it says is, like when we're dealing with two inputs, let's say L and K, if you fix the amount of the other input, the marginal product of an input eventually diminishes as its quantity increases. Okay, how do you interpret this? That means that if you have, right, L and K, let's say, that means that if I have marginal product to labor, that means I have to fix K constant, right? So when I increase L, right, my marginal product to labor will fall. That's what it means. And also it has to work not only L for all the inputs. So if I have to input, it also has to be the case where if I fix L instead and increase K only, then my MPK has to fall, right? Let's say that I have 3 different inputs, LK, and let's say that I have technology T, say T. Then all of these has to hold for for this law of diminishing marginal returns to be satisfied. Okay, so that means that, okay, let's say that it is L, K, and T, right? So these are held constants, and for this, L and T must be held constant. For this, L and K must be held constant, so on. So if you have like 10 inputs, then it has to, you know how to extend it to the more than 2 inputs. Okay, so that is the idea of the law of diminishing marginal return. So when you fix one of the inputs, the other, and you only increase the input of the other one, then the marginal product of that input has to fall, right? Which could be verified by taking the first order derivative of the marginal product of that particular input, right? And it has to be negative, right? So when L increases, marginal product, the change in marginal product have to decrease. So that has to be negative, right? Same here. Both of them has to be negative. And we know that MPL is actually come from the change, the partial derivative of the production function with respect to L, right? So you can actually change this a little bit and become like this, right? That is MPL, holding K constant. This is going to be MPK, holding L constant, right? Also, that means that you can have, this is pretty much just a second order derivative, right? Have to be less than 0. Or this one we also call it FLL. This one is called FLL, and this one is called FKK, or the second order derivative, FKK. That is a law of diminishing marginal returns. To verify whether or not this production function follows the laws of diminishing marginal returns, what you have to do is take the production function and do the second order derivative with respect to each input variables and check whether or not it is negative. That's it. If both of them negative or they are negative, then yes, we have a diminishing marginal returns, right? Okay. So both of them have to be negative. Now let's try to work out with this production function. So in the handout that I uploaded in Blackboard, it already show you how to solve it, the answer. So if you haven't had a look at it, at those answers, try not to look at it yet and try to solve this by yourself. So I'll give you maybe like, I would say like 5 minutes to be more than analysis is easy. 5 minutes for A, B, and C. Okay, let's see if you how much did you get, and can you verify whether or not we have a law of diminishing marginal returns. Okay, this takes 5 minutes. I'll come back. Okay, so I guess that you finished this problem. So could you please type in the chat what is the answer for A, B, and C? So A, compute MPL. So what does MPL equal to, and what does MPK is equal to? That's easy. I can just eyeball it from the production function. You can give me the answer straight away. MPL. Okay, thank you, Lachlan. So to the power, that's right. And MPK, everyone get the same MPL as Lachlan wrote? I mean, yeah, that's correct. Okay, so MPK, just the first order derivative of partial derivative of the production function with respect to L. We treat K as a constant, right? So with this, let's just take this partial derivative with respect to L. This MPL and the MPK would be now L must be held constant. We have half times L to the power 1/3 times K to the power of -1/2. So MRTS, right? MRTS is pretty much equal to the negative of MPL over MPK. So that gives us -2/3, right, times K over L. It's very simple, right? Everyone can see that. So if I, no, this is no, this has to be, sorry, it has to be -2/3. Made a mistake here. Okay, so if you take this down, then you get L to the power 1, and you put this up to get K to the power 1 up there. This is how we get this. This is MRTS. Easy. Okay, then we already get MRTS. So that is satisfy the law of diminishing marginal return. So what we need is FLL and FKK. So FLL based on this MPL, then FLL would be negative, right? I mean, you can just derive the whole thing, but it's very easy to see that this is negative. Okay, I can show it. I can do that. Okay, let me try to copy this. Copy this answer here. So I know that this one is FL, this one is FK, right? So I take another or the second order derivative of this production function with respect to L, or take another derivative of this with respect to L of this function. Then we get 1/3 times -2/3 times L to the power of negative, what is that? 5/3 times K to the power 1/2, which is less than 0, right? This one is positive, this one is negative, positive, positive. So that's why it's less than 0. Do the same to FKK. Now take the derivative of this function with respect to K. And we get 1/2 times -1/2 times L to the power 1/3 times K to the power -3/2, right? Positive, negative, positive, positive. So this FKK is also negative. So we have both FLL and FKK less than 0. So we have law of diminishing marginal return. Okay. Next, on effects and cross effects. So this FLL is called the on effect. FKK is our on effect. If we have FLK, that is called cross effect. Right? Let's say that I can take derivative of this function, but instead of with respect to L, now I take it with respect to K, right? That means that L is now a constant for this function, right? And K would be a variable, okay? Or I can take derivative FKL, which is this function with respect to L, right? So K is now a constant. In this case, in this particular production function is equal to, you either take this function with respect to K or this function with respect to L. So they give you the same function. And this function is called the cross price effect. So another way to interpret this own price effect is, what does it mean? FLL. FLL means that the change of your marginal product to labor when the labor unit changes, right? That would be the amount, the effect of L when L changes, how much it affects the change in the marginal product to labor, right? So that is like own effect. So when L increase, the same input L increases, fixing K constant. When L increases, how does it affect the change in the marginal product to labor? That is FLL. Whereas FLK is the cross price effect, where it would just it means when K changes, right? When K changes, so this is equal to the change in the MPL over the change in K, right? Whereas this one is the change in MPK over the change in L, right? So this one, it means that when K changes, how much it affects the marginal product to another input or labor, right? So it's called cross effect, because it's a change in K input affects how the marginal product to another input to labor change. FKL, when L changes, how much it affects the change in marginal product to capital. And that is called cross effects, FLK and FKL, own effects, FLL and FKK, right? When there are two inputs, L and K, in this particular scenario, right? Increasing the amount of one input may affect the marginal product of the other as well, right? Because this is the cross effect, and that is FLK and FKL. We typically assume that the magnitude-wise, the own effects are larger than the cross effects. Right? So this one, so when you multiply, this is the own effects, right? Multiply them together, it is larger than the cross effects, or this one times this one, less this times this has to be greater than 0. That means this one is bigger than this, right? And this condition is sometimes known as own effect is bigger than the cross effect. Now, remember that before I talk about diminishing marginal returns, the law of diminishing marginal returns. Now, for this slide, we will now talk about diminishing of MRTS. The diminishing of MRTS, which is not the same as the diminishing of MP, okay? So diminishing of marginal rate of technical substitution, what it means is we do have this diminishing MRTS. That means MRTS is a slope of the isoquant, right? MRTS is a slope of the isoquant, which is this, okay? It's what it means. If this one is a decreasing, so if this one is decreasing, so that means that when you take an absolute value, because we just look at the magnitude, right? It's going to be falling MRTS. Diminishing MRTS means falling of the, you know, the magnitude of the marginal rate of technical substitution. So along the same isoquant, along the isoquant, as the amount of L increases, the absolute value of MRTS decrease. Okay, the absolute value of this has to decrease. L and K, right? So we have isoquant taking the shape like this, convex to the origin, right? So you can see that the slope, right, is negative, but it becomes flatter as L increase. When L increase, we are moving towards the right hand side of the isoquant. So that means the slope becomes flatter and flatter, or right, the magnitude of this has to fall. When you have flatter, the magnitude is decreasing, and that is a diminishing MRTS. Look at the absolute value of the slope, the isoquant would decrease as L increases. Whereas the diminishing of marginal product is looking at, right, FLL, like how marginal product of labor changes when L changes, and how much marginal product of K changes when K changes, right? That is diminishing marginal returns. Diminishing marginal rate of technical substitution, actually looking the whole thing and see how when L increases, how does it affect the slope of the isoquant in the magnitude, in the magnitude wise, instead of, you know, the negative value. Okay, intuitively, holding the output constant, it is harder to substitute capital with labor as a K over L ratio falls. It is harder to substitute labor with capital as a capital labor ratio increases. The way to directly verify whether or not we have or we do not have the diminishing MRTS is that we need to see if we have three conditions or not. Okay, if we have three conditions, 1, 2, 3, then we can make a conclusion that we have the diminishing marginal rate of technical substitution. If we only have 1 and 2, but not the third one, then it doesn't mean that we do not have diminishing marginal rate of substitution. It doesn't mean that. So what it is that these three conditions would be like a sufficient condition to guarantee that we have this. But by not having any of these, it doesn't mean that we do not have that. Does it make sense? So it's just that if you can verify all three and we do have all three holds, then for sure we do have this. But if we do not have one of these conditions, it does not mean that we do not have diminishing marginal rate. So these three conditions are sufficient, but it is not necessary conditions for the diminishing marginal rate of technical substitution. Just guarantee that it would happen, but it's not necessary that to have diminishing marginal rate of substitution, these are the requirements. You know what I mean? So it's just one way, it's just kind of one direction that, okay, this implies that, these three conditions imply that, but these conditions do not imply this. I mean, this diminishing marginal rate of technical substitution does not imply these three conditions. Okay, so what are the three conditions? First, if we have diminishing marginal returns to labor, diminishing marginal returns to capital, and the own effect bigger than the cross effect, then it guarantees that the diminishing marginal rate of technical substitutions does exist, right? If we only have these two, but not the last one, then we may or may not have diminishing marginal rate of technical substitution. That doesn't, we just don't know. We need to explore a different route. Just like with these three, guarantee that we for sure gonna have this. Okay, so like the other way around is not true. Having diminishing marginal rate of technical substitution does not guarantee that the three assumptions above must hold, right? We only have this imply that, but this one doesn't imply these three. Any questions? Next, we're moving on to the returns to scale. With the returns to scale, there are 3 different kinds: increasing return to scale, constant return to scale, and decreasing return to scale. So the general idea is, for the increasing return to scale, if doubling all the inputs would lead to more than double of output. If doubling our inputs, then it will lead to the double the output. If doubling all the inputs, the output actually would be produced less than the double, right? So mathematically, to identify the relationships, you know, all the criteria for this return to scale, pretty much we can have, if we have L and K, right? As this is input for the production. So F to L to K, right? When we compare to 2 times F L K, right? So this function, what it means is, if L is equal to 2L, let's say L star is equal to 2L and K star is equal to 2K. So we double L and K, right? Then we see what are the outputs going to be like with using this amount of inputs, right? And the right hand, so the right term here, I mean, this is a double the amount of output. Right? So we can have greater, equals, or less than. So if we increase, if we double the inputs and the output from this doubling the input is bigger than twice, 2 times the amount of original output, then that means we have increasing return to scale, IRS. If it's equal, I have CRS. If it's less than, it's called DRS, decreasing return to scale. Well, you know, intuitively, you can think about, okay, right? If I am a firm, I increase my inputs. You know, let's say that I want to produce more output, right? So I said, okay, now to produce more output, obviously I have to increase the input. So let's say that I increase both K and L in the same proportion, like twice, like I double my inputs. Then does it mean that my output would come out double, right? It could be double. If it's double, then I have constant return to scale for this production function. But if actually I could produce output, the output yield is actually greater than the double, then actually this is good for me, right? And then we have increasing return to scale. But if I double the input, but my output is so bad, I mean, it increased, but increased less than 2 times the original output, then this is decreasing returns to scale. So this is the criteria to identify the types of return to scale for a particular production function. For example, I have this Cobb-Douglas production function in which I don't know the values or parameters alpha and beta, right? So suppose we double input from LK to 2L and 2K. So I have F2L, so I just replace 2L in my production function and replace K by 2K in my production function. So this is, instead of L to the power alpha, now I have 2L's, and both 2L's must be to the power of alpha, right? Just think of L as a 2L, like that new variable 2L instead of L, and then K, 2K instead of K. So from here, right, I can see that, okay, I get 2 to the power L times, to the power alpha, L alpha to the power alpha times 2 to the power beta, K to the power of beta. So I can add the 2 together. So the idea is I want to be able to to make a comparison between this and that, right? So what I need is I want to write this function as a function of just FLK, right? So this one has to somehow be a function of FLK, and then I can make a comparison. So, and that's the whole point, that I know that FLK look like this, right? So I try to rearrange the term in which it would give me this function as a function of FLK, right? That's what we need. So what we see here is, okay, now I have this, which is my FLK, right? So 2 alpha plus beta times FLK, right? So compare. Now it's comparable, right? You have F2L2K, which is equal to this. Can we say anything when we compare this one to this one? Is it greater, equals, or less than, right? So these two are the same. So the only difference is this. So there are three possibilities here. If alpha plus beta is equal to 1, then we have a constant return to scale. If alpha plus beta is greater than 1, then this one would be bigger than the right-hand side. So we have increasing return to scale. If alpha plus beta is smaller than 1, then we have a decreasing return to scale instead, right? And that's how we verify the return to scale accordingly. Okay, so let's solve 3 different kinds of production functions. So we have a linear production function, the kind of a perfect, it is perfect complement production function. So when you see min, you know, it's similar to the utility function where when we have x and y are perfect complements, right? You have to consume x and y in the same proportion because they are perfect complement at a certain ratio. So in this case, it could be interpreted that K, inputs L and K are perfect complements. So you need to, the firm has to employ the certain fixed, you know, fixed input mix between L and K, because L and K are perfect complements for this production. And then the third one is just the Cobb-Douglas production function. So again, I give you 5 minutes to work with A, B, C, and then you check later how it works. How did you be able to get to the final answer and the final conclusion? You know, derive your own work. And B is probably going to be a bit interesting because of the function that might not be that straightforward. But I don't want you to give you any guide. So I just want to say that let you think about how it is going to work. And it's okay if you cannot solve it, but at least give it a thought about how you can approach this kind of question with this like production function. Okay, give you 5 minutes, so I come back at 3:10. All right, did you guys finish all 3 ABC? So A, for A, is it increasing, decreasing, or constant return to scale? For A, constant. Everyone get constant? Yeah. What about C? So I'm gonna skip B. What about C? Yep, constant. What about C? Is it constant as well? Increase. C increasing, increasing. Yes, C is increasing. That's true. And what about B? Is B increasing, constant, or decreasing? Or couldn't solve it? Constant. Seems like Mengjiao and Haiyang can solve B, which, and then answer is constant. So okay, let's start with A, which is correct. So let's start with A. So the answer is this constant, constant, and increasing. Okay, so I start with A. It's really easy. So for me, I feel that it works better if I instead of like use 2 times. For me, I would prefer to use something like parameter like gamma or whatever, or lambda. I should put lambda. Okay, which is could be 2, 3, so anything that is greater than 1, right? Because you want to increase K and L at the same proportion. So it doesn't necessarily have to be double. It could be, increased by 1.1 or increased by 4 or something like that. And then so therefore my function would become lambda L plus 3 times lambda K, because if I put 2 instead of lambda, then it's not that clear when I use like just a particular value number. So with this, then again, I want to rearrange this term so that it looks like original function 5L plus 3K, right? So since I have lambda here, both left, this has to be lambda K, not lambda L. Why did it do that? So that has to be lambda K, okay? Sorry about that. So you can see that it is equal to lambda times 5L plus 3K, right? And this is my FLK. So that is equal to lambda times FLK. So this is exactly equal to that. So it's a constant return to scale. Okay. I come back to B, go to C first. For C, you may not necessarily need to derive this because this is the Cobb-Douglas function, and you know that with the Cobb-Douglas function, you just need to look at the power of K and L. The combination of these, if it's greater than 1, if this number plus this number is greater than 1, it's increasing return to scale. If it's equal to 1, it's constant. If it's less 1, it's decreasing. So 0.3 plus 0.9 is greater than 1, so it has to be increasing return to scale. So you can use that knowledge that that given that it's a Cobb-Douglas function, or you can derive it, right? Lambda L, lambda K, which is equal to 8 times lambda K to the power 0.3 times lambda L to the power 0.9, which would be lambda 0.3 plus 0.9 times 8k to the power 0.3 times L to the power 0.9, right? This is FLK. So this is equal to lambda to the power of 1.2 times FLK, which is greater than the lambda of FLK. Therefore, we know that this is increasing return to scale. Okay. For this one, okay. For this one, is the FLK. So the amount output actually is equal to, you know, the minimum value between these two numbers, right? So let's say minimum AB, right? The minimum AB is equal to A if A is less than B, right? It is equal to B if instead A is greater than B. If it's, you know, A is equal to B, then it's equal to A and equal to B, right? That is the how we measure this output based on this particular function. So if I say that I multiply, you know, the value of both A and B by lambda, right? Then my answer is going to be equal to lambda A if lambda A is smaller than lambda B, right? Or if A is less than B. Given that lambda has to be positive, you know, positive value, okay? This is equal to lambda B, right? If A is greater or equal to B, right? So if I know that if I multiply A and B by the same value, then the answer could be either lambda A or lambda B, right? Or pretty much this means it would be equal to lambda times minimum of AB, right? Because lambda A is lambda times the minimum of A if A is less than B, right? Or it could be equal to lambda B, which is equal to lambda times the minimum of AB if A is greater or equal to B. Therefore, this function has to be equal to this function. So you can just like take that multiplicable value outside this minimum function. These are equivalent. Okay, I just told you why this is the case. Okay, so if lambda L, lambda K has to be equal to minimum of 4 times lambda L times and 7 times lambda K, right? So lambda L, it is lambda K, okay? And so I can take lambda out. Let's take lambda out equal to minimum of 4L and 7K. I just take lambda outside since it is a common factor for both terms. So take lambda outside, equal to that. So this is equal to lambda times FLK. Right, so you can see that if lambda L lambda K is equal to lambda times FLK, so this function has to be a constant return to scale. And I think that is the last one. Anyone have any question? All good? All good, great. Thank you. Okay, if it's clear and everyone don't have any question, then I finish this Q&A now. And do not forget, Chang has a question. If it's max, it will be the same or not? Okay, that's a good question, right? So let's work together. So he asked, what if instead the production function, because we have the task, instead production function is the max. Let's say, just make it very simple, max L and K, right? Is it constant or not? Right, so you can say that, okay, max AB is equal to A if A is greater than B, and it's equal to B if A is smaller or less than B, right? So we need max function, yeah? So if I multiply X and B by the same value, right, lambda, lambda B, right? Then again, lambda has to be positive. Okay, lambda is positive value, so it's not dealing with negative because this is a return to scale. For the return to scale, then we double, we increase the inputs. But this only works when lambda is positive, right? Not that for any lambda, but for this particular context, it works because lambda is positive. But if we have lambda could be negative, then it's different story. Okay, it could be it could be a different story. So just keep in mind that this works because lambda is positive, right? So in this case, if lambda is positive, right? So you have that's going to be equal to lambda A. This is going to be equal to lambda B, right? If lambda A is greater than lambda B, if lambda A is smaller or equal to lambda B, or because lambda is non-zero, then we can reduce to this, right? So let's say, okay, so pretty much this is the same answer, right? So the max A and B equal to this, max lambda A and B equal to this, therefore this function must also equal to lambda max AB, right? Because it either can be A, and then the answer is going to be lambda A if A is greater than B, or it's equal to lambda B if B is greater or equal to A. So therefore, this has to be constant return to scale as well for the max function. Okay. Yep, that's an interesting question. So any other question? No question? Oh, good. Then see you again next week, and I will upload the lecture recording for lecture 10, and do not forget to submit the tutorial, that is due on this Monday, because you didn't have it that last week, right? So don't forget, we do have it this week. Okay, if no other question, then see you guys later. Bye-bye.